S is complex frequency. It has a decay rate and it has an oscillation. And the signal Es of t is just like E sigma plus J omega t. So it has two parts. The first part is the decay. And the second part is the oscillation. These will tell you how many cycles per second. These how fast does it decay. And depend on the value of sigma and omega, you will get different signals. And those are the different signals. So here, sigma is -1. Omega is 2 pi times 0 is 0. So what did you get? E -1 is a decay. No oscillation. You got this decay signal. This signal, sigma is 0. No decay. But omega is 2 pi pi. So that's an oscillation. That means 5 cycles per second with no decay. This signal actually has sigma -1 and omega 2 pi pi, or the frequency 5. So you get oscillation, 5 cycles per second, but with decay. Because of the -1, see how decay is flowing. This one has a decay, has an oscillation, and phase shifted. It shifted to the right by pi/4. Pi/4 means pi is 180. So 360 pi is 180. That's a shift of half cycle of the wave. So if you wave like this, you shifted half cycle. Pi/2, you shifted 1/4 of cycle. Pi/4, you shifted by that much, 1/8 of cycle. So this one, this signal here, is exactly this one, except shifted by pi/4. See, this is the start at 0, this is start here. So that part here now is showing up here. And this actually a signal that exponentially 0.5. So it's exponentially grow with oscillation 3. See how it's grow slowly. Now, if you add all these, you got this signal. Now the question is, you don't have this information. You don't have this information. When you record a signal like radiation from galaxy, or radiation from Earth, or you pick up a signal of speech, or you pick up a signal of temperature you are measuring, or a magnetic wave in the body, you don't know what's the structure of it. All you are seeing something like this, which doesn't make sense. Now the question is, I want to know what are the frequency content in this signal. That's what I want to know. What is omega here or here? What is the decay rate here and here or here? That's what I need to know. Why do I need to know this information? Because they're going to tell me about the mechanism of the system that generated, either the galaxy or the heart or the brain activity or muscle contract or whatever. By knowing this frequency, it tells me the mechanism of the system I am picking the signal from. Now the question, how do we get this information from here? That's what Laplace. See, Laplace transform, you take this signal, which is x of t, in the time domain, you do the Laplace transform, you will get x of s. Now x of s, you will get for different value of s, you will get a value, which is x. This is a function of s. So in this case, let's say this one -1, 5. So for s equal -1 plus j 2 pi, omega is 2 pi 5. So this is here. If I find x for this s special, let's call it s0. You will get a number. That number will be 1.5, something close to the 1.5. And they tell you this frequency is present in this signal, the Laplace, with a string of 1.5. That's the Laplace. If I tell you what is, does this complex frequency -4 plus J8, does it, oh, they don't see this part. They see up to here. Guys, speak if you don't see this.
This I'm supposed
I can't see.
Can they see this? You can.
I can't see it.
Guys, why don't you talk?
What are we supposed to like?
I don't know, I was writing something here.
I didn't know you were writing something.
Oh, I didn't have.
All right, I will just keep, not to move here.
I didn't even know
What I
about.
was saying, is, if I have this signal, that these signals, and I want to know, does this frequency exist or not in the signal? -1 plus J 2 pi 5. So this is my complex frequency. This is sigma, this is omega. And I want to know, does this exist in the signal X? When you do the Laplace transform, what you will find, because this signal exists here, you're probably going to get something close or near to 1.5. If I ask, what about this one, -8 plus J 2 pi 10? It doesn't exist in our signal. So if you do the Laplace transform of x of t, and you got x of s, this, you will get 0. And that's what's the Laplace transform. So basically, if I know the Laplace transform of a signal, I can reconstruct the signal in the time domain using this equation, this summation. So it is ESIT, which is, you view this 1, and this x of SI will be, in this case, 1 here. X of SI, another I, it could be 1, you will get 0.8. Another I, it could be 3, you will get 1.2. And if I sum all these, that means sum all these, I get back this signal. And just to make a link between the time domain and the Laplace domain. In the time domain, we said any signal x of t can be represented as a linear sum of these impulse response, and x of n of t will be the amplitude of the impulse. That means that's in the time domain. We said any signal I can represent it as impulses. If I have the analog, the continuous, then it's perfect, but everything is digital. So x of t can be represented as a sum of x instead of t. Now it's going to be like n of t or k of t, where k is a number, k1, 2, 3, 4. And this would be this amplitude or this amplitude or this amplitude, depend on the location of the impulse. And this is K capital T. And the capital T here, we call the sampling interval. So I take sample every 1 millisecond or every 2 milliseconds. So this is x of t. Any signal in the time domain is just a linear sum of impulses. The amplitude of the impulse is the amplitude of the original signal at the location of the impulse. This would be, if this is 5, this would be x 5t. And that value here, whatever this value is, times this impulse, which is t minus 5t. So that's in the time domain. Now in the frequency domain, which is this, it will be the same thing as a linear sum of this function, not impulse, this function. And this function depends on S, it looks like this. If S here has sigma, decay, it could grow. If S here has omega, it can oscillate or just a DC. And if I sum those signals of different string, x of Si, the Laplace is the string of these, I can reconstruct the signal x of t. Now, what does the system you design or the filter you design? The filter you design, this will be the input, x of t. And your system going to be manipulating these components, either improve, increase the value, or decrease. For example, if I want S1 minus 3 plus J4 to be enhanced, then the system will make this louder or larger. If I have a frequency which is a noise I want to suppress, somehow I don't want this, it doesn't interest me, then the system you will be designing here, that's the system, or this one, will suppress this frequency. That means that frequency, whatever it was, maybe it could be 10, the strength of it, it could make it just 0. So we explained this one in the time domain. If I have the input x of t, the impulse response h of t, then the output just convolution. In the Laplace domain, first I take the Laplace transform for x of t, so I get x of s. Then I process it with this system h of s. And I will get output y of s. What is it? Simple multiplication. X of s times h of s. And that's the advantage. Versus here convolution. Then how do I get back h of y of t? I do the inverse Laplace transform, I get y of t. Now let's look at the definition of the Laplace. When we say two-sided Laplace transform, the two-sided Laplace transform means the signal x of t exists from minus infinity to positive infinity, or it has a value at negative t and positive t. Then when I find x of s, in this case, I will use the two-sided Laplace transform. Why two-sided? Because the lower part of the integral is negative infinity. So I'm going to take all the Laplace transform with this side and this side. And that will be the two-sided here. Now, if the signal x of t causal, that means the signal only exists for positive t. So if this is 0, so the signal only exists in this region. That 0 could be the time you start making the measurement of the signal, or that 0 could be the time of turning on the system. Now, if you have a signal that doesn't have value at negative t, that's causal signal, and now we use the one-sided Laplace transform. That means we use these. And this is just exactly the same as this. The only thing is the lower limit of the integral is 0, because t here starts from 0 to infinity. Now, how do we get the inverse Laplace transform? So let's assume you have x of s. Oh, I can't write here. So you measure the signal, you got x of t, you did the inverse not the inverse, the Laplace transform, you got x of s. Now, s has two parameters, sigma and j omega. So if I plot the magnitude of these, it's going to be a plane where this is sigma, this is j omega. So you plot the magnitude, you're going to get a plane. So it's going to be, it could be, let's say this is the origin, and this is the plane here. And this is negative sigma, and this is positive sigma. Now, the magnitude here is going to be a plane, a surface. It could be high here, then decay slowly for large sigma, and the same here for large negative sigma. So that is x of s. It has different value here and here and here and here and so forth. So I processed x of s. I maybe filtered out certain frequency and amplify certain components. How do I get the inverse now? X of t. From here. It's a line integral, which we don't, if you go graduate school, you're going to learn about line integral. But line integral, you say, I will choose sigma here or here, it doesn't matter. And you have a plane now. And then you do a line integral for sigma, any value you choose, from minus, this is j omega, from minus infinity all the way to infinity. Take the integral, line integral, and then you will get value, and that will be x of t. And that's the inverse Laplace transform. C as any value for sigma you choose, as long as in the region of convergence. And you carry this, you will get x of t. Are we going to carry out this integral to find the inverse Laplace transform? No. So how did you find inverse Laplace transform differential equation? Anyone still remember? What did you do to get the inverse? Table, but you still have to do the partial, what they call it, partial fraction expansion. Like if you have h of s, something like this, s squared plus 4s minus plus 9s cubed plus 3s squared or something, you do the partial fraction expansion to terms that we can recognize on the table. Then we use the table to find the inverse Laplace transform. That's exactly what we will be doing to find the inverse Laplace transform. So we're going to do partial fraction expansion and the table. Okay. Let's take examples. Let's look at this impulse. Find the Laplace transform of this impulse. In the time domain, we may think of the impulse nothing, right? An impulse like this in the time domain, it just 0, 0, 0, sudden jump, then 0, 0. And now I need to find, if that is my x of t, I need now to find x of s. What is the Laplace transform of this impulse? Or what are the frequency content in this impulse? So we're going to follow the definition. What is the definition? X of s equal minus infinity to infinity, x of t e minus s of t dt. Is it e minus s of t, the definition? Let me just double check. That's the definition. So I'm going to use this definition. So that will be minus infinity to infinity. What is my signal x of t? It's just this impulse. And from here, an impulse time any signal, what do you get? You get the impulse back and the value of the signal at the location of the impulse. So the samples, this is just sampling. So you're gonna get the impulse back, time whatever this function equal at the location of this impulse. This impulse exists at t equals 0. So then this will be E minus S 0 dt. And one more step here. Now these just equal 1. I will not put it. Let's plug 0, this is 1. And now the integral of an impulse is just the area under the impulse, and we said that area is 1. So x of s equal 1. What does that mean? You have in the time domain an impulse that exists for nanosecond, just went up and down for a short period of time. The frequency content is 1, x of s. If I plot that, that means this is sigma, this is j omega. It does not matter what is sigma, magnitude of x of s. It does not matter what is sigma, what is j omega, the value is going to be always 1. So if I say this is my plane, this is sigma, this is omega, then the frequency is just a plane 1 unit up the floor, and it's just an infinite plane. That means that impulse has all frequency content, all frequency content, DC, 1 hertz, 2 hertz, 3 hertz, and all fluctuation. They're just simple impulse. And that's why when you excite a system, you want to see how the system responds to different frequency. You excite it with an impulse because you are really inputting to the system all, by that one impulse, all different frequency content at instantaneous time, at one time. It's very difficult to visualize. A simple thing like this will have all this frequency content. But if you think of it, the rate of change, frequency represents rate of change. That's huge rate of change. From total 0, suddenly jump high and come back again. That has to be a high rate of change. And we will see in one of the last labs, when we do the Fourier series analysis to create this periodic signal or this periodic signal, it's a linear sum of sinusoidal. Maybe you're going to add 100 sinusoidal, and you will get this. Yes, 100 sinusoidal or cosine function of different frequency, you will get these. Same thing here. But to get these,
we can't really see that over there.
oh, you can't. Oh, guys, remind me. Okay, okay. What I said is in one of the lab, if I Fourier series, see, the question is, it's just very hard to imagine an impulse like this will have all these frequency content. But in the lab, you will see to generate this periodic square or this periodic triangle, all you need is sinusoidal of different frequency. And you're going to just add maybe 20 or 30 or 50 frequency content. And you will get these and these. So basically, you're going to add these. Then you add higher frequency. Then you add higher frequency. And when you add them up, maybe 50 components, all you need. And you will get these. Or you will get these. But those will be different amplitude, different frequency. But if I ask you to generate this one, you will see to get how many of these to add to come up to here, 1,000 because you need 1,000, 2,000 frequency content by adding them to get this one. And that's what one of the lab will show you that impulse, even though it's very short in the time domain, it has a large frequency content. Okay, let's do then the unit step function. Let's do this example. So again here, we have this x of t is a simple unit step function, u of t. If you plot it, it looks something like this. And we need to know what is the frequency content of this one. Well, we're going to use this definition, x of s equal minus infinity to infinity, x of t, e minus s of t dt. The signal here, x of t, exists only from 0 to infinity. So the limit will be from 0, that's the lower time where it exists, all the way to infinity. Because this is just u of t keep going to infinity. And what is it equal in this range of time? Just 1. And that will be, if I integrate this one, my variable is t. So that will be 1 over minus s, e minus s of t, 0 to infinity. And if I do that, it's minus 1 over s, e minus s, infinity, minus e minus s plug for t0. So I just plug for t infinity and plug for t0. Now, you gotta be careful. See, this is easy. Doesn't matter what is s. Anything multiplied by 0 is 0. So this is 1. Now we have a problem. We have to be careful. Here, look at the following. I can rewrite these as the following: minus sigma plus j omega infinity. This will go to 0 only if what? I can rewrite the whole thing here. E minus sigma times infinity minus j omega times infinity. So this can be written like this. Now this equals 0 only if what, guys? Here, this term is just going to oscillate, right? J omega is just going to oscillate for infinity. This is the important term. So this will go to 0 only if sigma equal what? There must be a condition for sigma. It's sigma minus 1. Can this go to 0? Yes.
Has to be greater than 0.
Has to be greater than 0. Because if sigma is minus 1, minus 1 times minus positive 1, time infinity, positive infinity, this go to infinity, and that limit doesn't exist. The Laplace transform doesn't exist. So the only way this x of s will exist if this term here goes to 0. And the only way for this term to go to 0, sigma has to be positive or 0. So sigma has to be positive, larger than 0. Or you can say the real of s larger than 0. Because the real of s is sigma j omega, the real of s is sigma. And that's what we call the region of convergence. That means u of t will have a Laplace. And that Laplace will be now If this condition is true, then this will be minus 1 over S, 0 minus 1, that's 1 over S. And you have to specify this is true, or you say region of convergence, real S, or sigma, that's fine, real S larger than 0. Make sure you write that. Now, if I ask you to plot these, to plot the magnitude so this is sigma, this is j omega, and if you plot the magnitude of 1 over S, which is the magnitude of x of S, let's write 1 over S. 1 over S is the same as 1 over sigma plus j omega, right? Because S is sigma plus j omega. Now the magnitude here will equal 1 over the magnitude of the denominator, because the denominator is complex. So that will be the square root of sigma squared plus omega squared. So if I plot these in this plane, first, sigma cannot be 0, right? Because that's what we said. These exist, the region of convergence, real S is larger than 0. That means sigma is larger than 0. So that means this plane here is out of the question. The region of convergence only here, because sigma has to be larger than 0. Now, if I plot these, as sigma gets larger, this quantity what? Gets smaller. And or as omega gets larger, this quantity gets smaller. So if you plot this using MATLAB, you will get a plane. Let's say it's gonna be, let's say this is the origin. The plane gonna be like this way and this way and this way. So it's going to be like a plane that goes to the origin and increase high. So basically it has a lot of low frequency component and high frequency component. It just this goes.
Professor,
Your mic is off, Professor.
but my cat walked across the keyboard and muted you. Could you unmute yourself?
Can you hear me now?
Yes.
So you didn't hear anything before?
No, just for like, I don't know, a couple of seconds.
Or just a couple of seconds it turned itself off?
Yep.
I think I'm gonna go back to my laptop, my iPad, but in the class. So instead of writing here, I will be writing the iPad. So in the class, we'll see it here. So just 2 seconds, guys. Are you sure?
Yes.
All right. I'm gonna stop here. But basically, if you plot the magnitude, that's what it is, and that's what the Laplace transform. So next class, we're gonna take more examples, and I'll see you on Friday. Hold on. Any question, guys? Do you have any question?
So the plot of this, there's a spike like right around the origin and then it decays exponentially down in all directions.
Yes.
Okay, I was just making sure I was visualizing that right.
That's why we can, it has to be larger than S, because you put S 0, that means sigma 0, omega 0 is go infinity. So, but as you get closer, just go for it.
I was trying to catch up with my programming lectures, and so I still have more. So